All right, so these are my video notes for my class CIS352 Spring 26. This is the second lecture. This is lecture 2. And I'm just going to do a quick recap about what we talked about throughout the class. So we talked about various forms. Remember, forms are the primitive foundations of syntax in the Racket language. So the forms are the things that give us the real built-in behavior of the language. And there's a relatively small number of forms. One of them is the define form that allows us to define values and functions. So we talked about here on line 24, I've got a definition of foo that's 42. And then I've got my function of x. Remember, when you surround something in parentheses, that defines a function call. All right, so define is a special form. We talked about the fact that in general, if you have something surrounded in parentheses, and if the thing that immediately succeeds that parentheses is not a special form like define or if, then it's generally a function call. So in this case, I wrote out an expression, I fully parenthesized it, and I said, how can we define f of xy? We defined it like this. Okay. Now, environments nest, and so the environment is the thing in the language. An environment is an abstract concept, but it's something that associates names with the values at a pertinent point in the program. And so there is such a thing as both a static or lexical environment, meaning what variables are in scope or are defined in play at which static points in the code. So, but there's also dynamic scope, this idea of when you get to a certain point in the program, as the program's executing, a variable is assigned to some value, right? And so here on line 51, I've got this inner binding, this inner definition of plus that overrides the built-in definition of plus. And then outside of that scope, because definitions and defines create these new scopes, outside of the scope here on line 52, plus is in the environment, but it's the Racket built-in plus. It's not the inner definition of plus right here. Okay. We talked about cond, which is a form that is derived on top of if. And I showed this example of the Fibonacci implementation. So this one is exponential time. And I discuss an optimized implementation that uses a so-called a helper function. A helper function is a function that is defined under another function for the purposes of basically doing the hard work of the function. This is going to be a pretty typical idiom we're going to see. So I'm not really going to explain exactly how the algorithm works here. The basic idea is that we're going to use a few extra arguments as what are called accumulators. And across the course of the recursive calls to H, these accumulators will evolve. And so this is a sort of a pattern called tail recursion. It has a relationship to the sort of normal recursion that we'll talk about later. But in this case, really what I'm trying to show is not necessarily the algorithm or tail recursion or anything like that. I'm really just trying to show the fact that here we have an inner definition of H, which is kind of like, it's something that takes some extra arguments. So the user of optimized fib doesn't need to understand that we're using this inner helper function H here. We just want them to pass X, the argument or the number that we want to get the Fibonacci, sort of nth Fibonacci number of, right? But because of the way that H is written, we need some extra parameters. So we need to be tracking these two accumulator values. If we talk through how H works, we would find out that that's the case. And so to sort of isolate the call, to isolate the definition of H, because users of optimized fib don't need to understand we're using this helper function, we can kind of nest it right under here so that we don't pollute the namespace. And this is kind of a nice stylistic thing to do that often if you're a sort of somebody who's taken a functional programming class before, you might be familiar with this idiom of helper functions. That's something that I would say really you should be leaning on as you're starting to do your implementation here. I gave a challenge in class, a quick answer challenge. A student very thoughtfully pointed out that I should be working these right after I do it. So that's something that was my bad. I should have been doing that. So let's just start to work them out here. So for every con, we can replace it by an if, can't we? So we can say f of x, then it's going to be that the branch fires. Otherwise, we're going to do another if, g of xy, then the branch fires. That'll be z else x. Great. So that's Baz, and we rewrote it. Good. Then I talked through this example of basically how can this code be given a sensible meaning, right? I talked about the idea that if you just surround things in parentheses in Racket, that means call a function. So this means call the function a1 with 0 arguments, take its result, call it with 0 arguments, take its result, call it with 0 arguments. How can we make that work? So I wrote a definition. So I said, okay, well, a1 is the function a2. a2 is the function a3. a3 is the function of 0 arguments, which returns 15. And if you do that, you can get this to work out just fine. Okay, but in general, you should be very careful to start putting parentheses around things in Racket, because it doesn't mean the same thing as it does in other languages. In other languages, you use parentheses for disambiguating grouping and things like that. But here, every parentheses is semantically relevant. Okay. Okay, so then we started talking about lists and recursion. I really just started to introduce lists in this class. I really took a whirlwind tour through them, and they're not finished, basically. I'll keep talking about them early next week. We talked about the fact that in Racket, every list is basically canonically represented as a linked list. And so the list 1, 2, 3 is actually the list of cons of 1 followed by the list 2, 3, where 2 starts with 2 and is followed by the list of 3, an empty list. And then this thing right here, cons 3 empty list, is the singleton list containing 3. And so if I evaluate this in the REPL, if I do cons of, ooh, I've made a mistake here. Let's just comment that out. And we'll comment this out just to make things work. Not sure what's going on here, but I want to get to a good state. Okay, so here we go. If I do cons of 3 in the empty list, I get the singleton list containing 3. So that's in memory represented as, right, so the list of 3, which is equal to cons 3 empty list. This is the list that's represented in memory sort of like this. So there's a con cell. And then I've actually got this pointer right here. This thing right here is in the car position, or in the first position, is 3. And then in the cutter position is a pointer to the empty list. So that's what this looks like in memory. And at runtime, this empty list value is actually just some canonical pointer, like null or something like that you might think of in C. It has some known value, let's say. It turns out that also a little piece of trivia is that in Racket, numbers are not represented in a fixed size representation. And so it's not that 3 is literally sitting here in the first spot of this con cell. It's actually a pointer to the number 3, where then that pointer is allocated out somewhere on the heap. So we'll talk about that as well when we talk about how data is represented. Okay. Just make some comments so I can run these. Okay, so then we talked about some interesting syntax for working with lists. So I give a few of them here. Empty checks if it's empty. Cons lets me prepend something to a list. Empty list is a literal that I can use anywhere. First gets me the first element, and rest gets me the rest of the list. Okay, so let's do some actual exercises to push on into next time. Okay, so the first exercise is going to be zeros of n generates n zeros in a row. And here I'm going to say if equal n 0, then this is the empty list. Otherwise, it's going to be cons of 0 and zeros of n minus 1. Okay, so that's zeros. Let's see if it works. Okay, good. What about another one, which is going to be repeat I n, and this is repeat I n times. Okay, so this is going to be if equal in 0, then empty list, otherwise cons I repeat I n minus 1 times. Okay, so repeat 5, 12. Okay, looks good. What about range of n? So this produces 0 to the n minus, or maybe let's say 0 to the n. Okay, so this is going to be range of n here. So what do I want to do? So, okay, the natural way of writing it is actually going to do it in reverse. So the first thing I might try is I might try to write something like this. I might say if equal n 0, then make it the empty list. Otherwise do cons of n and range of n minus 1. So that gets me 5, 4, 3, 2, 1. And then here, maybe I should have it be the singleton list. I could do that. But this feels a little bit hacky, doesn't it? So this is not quite what we want. So what could I do? I could say... I could have another number here that I count up with, right? So as I count from to n, I could start I at 0. So the basic idea is use recursion with 2 parameters. N, end and I. I starts at 0 and counts up. When I equals n, return. Otherwise, return cons of I and the recursive call h. So we're going to make a helper function. Call it h. N and then plus I1. And something like this is going to be what we want. There's going to be some particularities. So let's, I guess peculiarities is what I meant to say, isn't it? H of I and then N. And then here I'm going to say if equal I and N. I think in this version I still wanted N. So I could either stop at n minus 1, or I could do cons in empty list. Otherwise, I'm going to do cons of I, or no. I is the thing that counts up. I can do cons of I and h of I plus 1, and then n. And then, of course, realize that here, when we call h, I can do h of 0 and n. But I can also refactor this program, because since I'm just threading the n through right here, I could just, by virtue of having this define sit under this define, I could just get rid of this parameter n right here. So I'm going to redo that in a second, but let's do it like this for now and just see that it works. So let's do range of 10. Okay, there we go. So that gives us the behavior we want. I think actually in Racket, the behavior is n-1. So let's make it do that. Because this is a built-in function in Racket as well. So now if I do range of 10, I get this as expected. And then let's make this refactoring that I said, which is to change h right here. We'll eliminate n. Now this n just sits at this scope right here. And then we'll get rid of this n because we don't need it anymore. And now let's make sure that it still works. Okay, there we go. So that's one way of doing it. There's other ways of doing it as well, but I think it illustrates the idea of kind of using a helper function. So, all right, we'll be back in class with some more examples next time, but hopefully these will get you started.